Now, we will start with our first speaker, main speaker, that is Gustavo Deco. We are very, thank you that he was able to participate. And now I have like the impossible task of introducing Gustavo in just a few minutes, so I will try my best. Gustavo is a professor at the Catalan Institution for Research and Advanced Studies and a professor at the Pompeu Fabra University, where he led the computational neuroscience group there. He was also the director of the Center of the Brain and Cognition there for 20 years. He's an associate researcher at the Max Planck Institute for Human Cognitive and Brain Science, and an adjunct professor at Monash University in Australia. And Gustavo has a PhD in physics. He has also a PhD in computer science. And because we all know that having an even number of PhDs, it brings bad luck, he also has another PhD in psychology. And Gustavo has devoted his career to understanding the computational principles underlying the human brain, using theoretical tools from dynamical systems, information theory, complex networks, and many other areas. And he has two great contributions to that. So I'll leave you with Gustavo. Thank you, Gustavo.
Yeah, thank you. Thank you very much, Gonzalo, for the kind introduction. Thank you also all the organizers, Gonzalo, Pascal, Andreas, and Christopher, for inviting me. It's really a pleasure and honor to give this talk. It's a shame that I cannot be there in person, but as you know, June here, at least in Spain, is a very busy month at the university. I have lectures and examinations, and it was impossible to travel. So I'm happy to be able to give this at least online. So the title of my talk today is Thermodynamics of Mind. It's a little bit provocative, but I will try to explain you what we mean with that, and you will see it's something really very, very concrete and we think very useful. It's a work that we were developing together with this with these two guys, Johnny Sanspel, also at my university and in Paris, and our also long-term collaborator in Oxford, Morten Krinkelbach. So let me try to motivate first. I mean, which kind of question are we trying to address and to answer? As you know, historically, I mean, in neuroscience, probably during the last century, I mean, we were extremely influenced by Ramon y Cajal ideas, namely that computation is absolutely local. Then during the last 30 years, perhaps with the advance in the technique for characterizing global activity of the brain, like the ones that are the focus in this workshop of fMRI, EEG, imaging, we came to the idea that, well, perhaps the computation is not so extremely local attached, but is distributed, because we have seen at the level of the global dynamics that really there are effects across space and time which relate the whole brain. But are mainly correlational studies, and therefore the next step is really to go more consequent in the direction of this extreme distributed computation idea. And one way of going in that direction, or one key question that we try to solve in that context is, okay, if the computation is extremely driven, then how is organized? So the key question is really about the hierarchical orchestration and organization of the brain dynamics and the different situations. Different situations mean different cognitive situations, the solution during the performance of different cognitive or perceptual tasks, or even during different brain states like wake and sleep, or even involving a different type of disease, how the hierarchical organization change in disease. So the most natural way of trying to characterize, to quantify this hierarchical organization is clear. I mean, measure the information flow, the functional interactions, so good as you can, and then just concentrate on the asymmetry of those functional interaction. Why? Because we know if all the functional interaction are absolutely symmetric, then probably this corresponds to a very flat type of hierarchical organization, very democratic. And the more asymmetry we observe in the information flow, the more orchestration, the more hierarchical organization we have. The problem is that for assessing this functional interaction, it's not so easy in some cases, because we don't have so many data. For example, the more clear example is when we use fMRI, where we know that because of the sampling rate and the time that we need to collect the data and the number of sessions and subsets that we need is at the end of the day, we don't have really so much data in order to have really good characterization of the functional interaction. In some cases, it's possible. And therefore, we were looking for an alternative, and the alternative comes from a thermodynamic idea, which is strongly related with this idea of the asymmetry. If hierarchy can be measured as or can be revealed through the level of asymmetry in the underlying functional interactions, this is related with the key idea in thermodynamics, which is called the detail balance, or the breaking of the detail balance. Namely, the breaking of the detail balance is exactly that. It's a measure of the asymmetry. And now we can relate this breaking of the detail balance, which is characterized in the hierarchy, with all the others associated thermodynamic ideas. Namely, as we will see in more details during the next slides, that the breaking of the detail balance is equivalent to the idea of quantifying the level of non-equilibrium, and the level of non-equilibrium is extremely associated, strongly associated with the idea of non-reversibility. In other ways, with the idea of having an arrow of time, in our case, in the brain signals. So that at the end of the day, by characterizing the arrow of time in brain signals, indirectly we characterize the non-equilibrium and the breaking of the detail balance. In other words, we characterize the level of asymmetry. In other ways, and that is the main take-home message, we characterize through the arrow of time in brain signals the hierarchical organization, and we can quantify in this way how this hierarchical orchestration of the brain dynamics is changing under different situations. And of course, all this analysis in the main part of my talk will be model-free, just based on this implementation of these conceptual ideas coming from thermodynamics. At the end of the talk, I will go into the direction, okay, now that we have the right measures, some property of those measures, we will try to explain that from a causal mechanistic point of view, meaning that we will try to use models, in our case, whole brain models, trying to explain, to fit the emergence of this hierarchical organization, and in that way we will get a mechanistic, basically, understanding of what's going on. Okay, that's the general motivation. First, before we start really with the thermodynamics concept, I wanted just to show very rapidly in this slide the alternative, the direct idea, what I mentioned at the beginning. Okay, let's try to characterize hierarchy by measuring explicitly the information flow and analyzing that with your favorite topological characterization. And we have done that in that paper in Nature Human Behavior, together with Diego Vidaurra and Morten Kringelbach. In that case, we use a kind of Grange causality. Actually, it's the transfer entropy, is an information theoretic version of the characterization of the information flow, which is pretty refined. I mean, we use surrogates, we normalize it, a lot of technical details, but the idea is to use this quantification as a direct quantification of the functional interaction. And then we use this in the context of the human connector project, as you know, over 1,000 participants, fMRI in different conditions, namely resting, and 7 different cognitive tasks, which are covering on purpose, basically the main aspect of the cognitive domain. And then if you measure that and you render that the top members in that hierarchical organization, characterized through this kind of Grange causality, then we discover all these regions. And the beauty is that if you do the intersections, it's a little bit more than an intersection, but just let's think of an intersection as a proxy of all these top regions orchestrating in each of those cases the activity, then we see that there are a set of key questions, which are rendered here, which basically run the whole show always under all conditions. And this is strongly related with the typical concept of hierarchical organization in the brain that were proposed many years ago, so originally by Bars and then refined by Stan Dehen and Jean-Pierre Chanchot, which is the idea of the global workspace. As you know, it's a theory of organization, of hierarchical organization of brain activity, but it's not quantified. So basically, with this idea of quantification of the information flow, that we can discover really who are those guys which are the global workspace, which are here the intersection of the top guys running the whole show under all these conditions. Okay, the problem is that in order to calculate this range causality, as I said at the beginning, or some replacement, and it's another way of characterizing information flow, in general, we need a lot of data. In this case, it was possible because it was the Human Connectome project, but in most of the cases, you know, we don't have so many data, and therefore we were looking for an alternative. And the alternative comes from basically this idea of thermodynamics that I was mentioning at the beginning. Just in order to motivate that, actually, the idea is not new. The idea was already exposed very nicely by Werner Schrödinger in his book, What is Life? A beautiful book, basically associating the ideas of non-equilibrium and consequently, as we will see, the idea of irreversibility or the emergence of an atom of time with the idea of life, of having a living system. And that was very influential and created really a whole new field of research, which perdures still nowadays, but basically at the microscopic level, basically related with the molecular biology, proteomics, and things like that. So what we are doing is trying to extend or to apply those same ideas, but at the macroscopic level of whole brain dynamics. So let's cartoonize, and I try to give you a feeling of the key ideas. So we mentioned at the beginning, I mean, and you can imagine, for example, a physical system, whatever. I mean, in our case, of course, will be the brain, but whatever physical system we have, if the information flow is symmetric, then we know from the thermodynamic analysis of that system that this system is in equilibrium, is, of course, by definition, non-hierarchical, because there are no one which is more important than the other. So it's a democratic, flat hierarchical organization. And that system is not producing entropy and has a very important characteristic, which is there is no one arrow of time. So the system is fully reversible. On the other hand, if you start to break the symmetry in the information flow, then automatically you create a hierarchical organization. And this creation of hierarchical organization is concomitantly produce an increase of the so-called production entropy, and the production entropy also evidence that emerge an arrow of time, meaning that the system is non-reversible. In other ways, if you look at the time evolution of the signal of system, let's say that the system is really the brain, so of your brain signals in one particular region with one particular methodology, it's not attached to any kind of methodology. It could be fMRI, could be EEG, could be even single neuronal activation, and then you see the evolution as you measure forward in time, and then you create artificially the reversal of that. So you just flip the time backwards. So it means that you can distinguish that. So in this case, and you cannot distinguish that in that case. So that means that one way of characterizing hierarchical organization could be by measuring the production entropy, and that was proposed in the lab of Danny Bassett by Christopher Lin a couple of years ago, and nicely published in PNAS. The problem is that, of course, if you need to calculate the entropy production for a multidimensional system like the brain, even in a low parcellation, let's say in a coarse parcellation of 60, 100 brain areas, it's a high dimensional space, and to calculate an entropy in a high dimensional space is of course impossible, and therefore you have to do some trick. I mean, the standard trick is, for example, to reduce dimensionality with PCA, principal component analysis, to 2 dimension, and then estimate the entropy. But that is not so satisfactory because it's a strong approximation. So what we decided to do is to do the alternative measure. So to characterize directly, quantitatively, the level of non-reversibility. And this is what we will do. First, for those of you who are not from physics, I just wanted to give you a very concrete image of reversibility and non-reversibility. And it's very clear with these two movies. On the left, what you see is a movie that is highly non-reversible. So there is a very clear of time. It's a ballet in pinging of a glass of wine, a shame per se, by the way. When you see the forward movie or the backward movie, it's very clear that they are different. One is the forward, one is the backward. You can distinguish them very clearly. On the other hand, if you have a system like this colliding billiard balls, it's perfectly reversible. And if you see the forward movie on the top of the backward movie at the bottom, you cannot claim or say or distinguish which one corresponds to the reality. So they are perfectly reversible. There is no 1 hour of time. Nevertheless, there are cases where the distinction is not so easy, and that will be the case of the brain. I reflect that with this movie, or an example of the movie of Christopher Nolan. By the way, the worst movie of Christopher Nolan, and I love Christopher Nolan, Tenet. But it's a good example for us, because in this example of the movie, what you see is that there are some people traveling forward in time, some people traveling backward in time, and it's very clear. It's like the glass of wine that we have seen before. It's very clear to distinguish who is forward and who is backward. On the right, what you see is the simulation of a system. It's a physical system. It's a spin system that by construction is non-reversible. So we know that the system is non-reversible. And here what you see is the evolution of some observables in time, and one is the forward and the other is the backward. Even if we know that they are by definition distinguishable, because the system is non-reversible, so we should be able to distinguish them. It's very clear that it's not so easy to distinguish them. And that could happen, and of course, this is what happens in the case of the brain. So we will use these ideas that we will characterize the level of non-reversibility, but we know that some cases are very easy to distinguish them, like the case of the glass of wine, like the case of Tenet, and some cases are not so easy to distinguish the forward and the backward direction in your signals, and that is the case of the brain. And therefore, what we use is a trick that was proposed by Jasinski, namely, in the first implementation of this idea that we call on purpose Tenet, but you will see that in our context will mean something different. It's a model-free machine learning framework, and the idea is very simple. Basically, we take our signals, which could be at different levels and with different methodology. Let's imagine, for example, now one concrete brain area, ball signals, fMRI. We have the forward version. We create by hand the backward version, and given that we know who is whom, we can train now a deep learning classifier in a supervised way. And basically by testing the performance of this classifier, if it is high, means that we can distinguish them. So that means that the system is non-equilibrium, it's non-reversible, there is an arrow of time, and what is more important for us, the system has a strong hierarchical organization. On the contrary, if the system has a low performance, then we have a very flat hierarchical organization. And of course, you can do that. We do this in this case with the slicing windows, and we can do that at the global, at the network, and the local levels. I will show an example of the global and the local level. And the classifier is what we call Tenet, is a deep learning classifier, which means that the temporal evolution, a deep learning network. And basically, we quantify the hierarchy by the performance of this classifier. So let's see some results. This is again the HCP, the Human Connectome Project, as I said, over 1,000 subjects under different situations, rest, and 7 different cognitive tasks. And what you see, just concentrate mainly on the left, is the level of non-reversibility or the level of non-equilibrium, or as I said, what is more important for us, the level of hierarchical organization. And what we get is really an expected result. That's under resting conditions. We have, of course, a hierarchical organization. The system is not flat, but compared to the other conditions, it's the flatter system. So it has the lower level of organization. There is a each dots are really the generalization subject. So you see that there is a high dispersion. And it's very interesting to see that when you start to do something in concrete, some cognitive task, of course, then you have to create more asymmetry. You have to create more hierarchy, and that is directly reflected in this quantification of the level of non-equilibrium reversibility. It's very interesting to see that, for example, the social task is the one with the most asymmetric, with the most hierarchical organization. On the right, I don't want to explain that too much. It's just because we are calculating this in Windows. It's also nice to see that this level of non-reversibility is very variable across the sliding windows, and in fact, there are also significant differences, but I don't want to do a big point from that. Another example where we see now global and local analysis. So the whole brain is a neuropsychiatric case. It's the UCLA database where we have around not so many participants. In total, there are less than 200. Some groups are controls, healthy controls. Some other groups are bipolars, attentional deficit, and schizophrenia. And what we see at the global level is that in general, under resting state conditions, the hierarchical organization indices in all the 3 diseases goes down. And even more, if we go and apply exactly the same strategy at the network or at the local level, as is shown here, and for example, just concentrate on the bottom where we contrast the local level in the different situations, just referring to the healthy situation, then we can see who are the drivers, who are really the regions which are creating this asymmetry, and it's really driving the arrow of time. And some of them have, of course, many useful interpretation. I have no the time here just to go into the details, but for example, just to give you a feeling, in attentional deficit, for example, you see that the main driver are somatosensory regions, which is very meaningful because means that they are really driving the whole brain dynamics. And perhaps this is the reason why people are not so attentive, because they are distracted by what's going on in the environment. As a second alternative, because of course the machine learning approach is also pretty heavy and also requires a lot of data, not so many as the direct evaluation of the function interaction, but it's also very computationally expensive. So we try to simplify our model-free approach, and we came with an idea that, as you will see, is extremely simple. We call that inside out, and it's just based on a correlation. The idea is exactly, the concept is exactly the same as before, but instead now of characterizing the difference between the forward and the backward version of the signal, we do an analysis which is pairwise based. It's a restriction. So let's analyze, for example, 2 regions to 1 pair. And the idea is to compare a shifted correlation in the forward version of these 2 signals and in the backward version of these 2 signals. So by shifting the correlation, so by shifting the signals, you can see here practically on the right, schematically, if you have these 2 time series in 2 regions, and then you shift a capital T time, then you break the symmetry. And then if you compare this breaking of the symmetry and by calculating the correlation of this shifted version of the signal in the forward condition respect to the backward condition, and just do the difference of these two correlations. If this is different from 0, means that you have an error of time. And of course, in order to do this at the whole brain level, what you do is to do exactly the same, but in a matrix. So for all pair-wise combination, and basically this measure done element-wise, so it's just the norm of the matrix. It's then out that this works very well. In order just to give you another example of another modality, another species, I took in this case different brain states. Instead of rest and cognition, is a manipulation of consciousness in monkeys. It's a public database where we have ECOG data in 4 monkeys. So it's also another type of measure, more directly related with the electrical activity of the neurons. It's just half hemisphere. And there are these manipulations. This is observed in 2 main manipulation of consciousness, namely comparing awake with sleep or awake with different application of anestheticon, and they use 4 different anestheticon. And what you see here, the main results on the right, in the form of violin plots, the level of non-reversibility or non-equilibrium, or what is more important, again, the level of hierarchical organization is always significantly higher in consciousness respect to non-consciousness. For example, when you compare awake and sleep, and this is just the difference of the shifted correlations at the whole brain level, and very nicely you see highly significant different hierarchical organization between consciousness and unconsciousness. When you look then at the different anestheticon, in this case, the beauty of these experiments that you can see also how they recover from the anesthetic. For example, when you use propofol, then again, same effect with the loss of consciousness. In this case, driven by the anesthetic, when you go down the hierarchical organization, when you recover, you go again up in the right direction. The only exception is when you use ketamine, that is going exactly in the other direction. And as you know, that is well known because ketamine is not a genuine anestheticon, and probably is the reason why some people use that as a fun drug nowadays. Another applications, again, back to fMRI. These are data from Paris and Liège, coma patients, which are controls, minimal consciousness state, and deep coma. And what you see is that the inside-out analysis of non-reversibility, so hierarchical organization is showing exactly the same. So it's a good biomarker, or a good measure of consciousness, which is, in this case, as I say, it's extremely simple to measure and takes really seconds. So I wanted to present now the mechanistic part. So now that we have some measures, and I will concentrate now in the easiest measure, the inside out, we can try to explain that from a mechanistic point of view, and for that we use a model. As you know, a model, a whole brain model, is basically a way of linking the underlying coupling, physical coupling, the underlying anatomy, with the functional activity, in the way as you characterize a functional activity. It could be fMRI, EEG, and there are many ways of characterizing functional activity. Usually what we do is we try to explain with your favorite model. In this case, I will use Stuart Landau oscillator, because we have shown in the last years that really is a very good model for the local dynamics. And by coupling this mixture between noise and oscillations with the anatomy, usually we use that for explaining the functional connectivity. But in this case, instead of doing this, we will fit the matrix, the inside-out matrix. So the matrix of non-reversibility. And even more, we will use really parameters for each pair connections. so that at the end of the day, what we will infer from here is masked by the anatomy, masked by the existing connections, the values of these conductivities in each pair, which give rise to the right level of hierarchical organization, as characterized indirectly through this thermodynamic trick of non-reversibility. So at the end of the day, we get a mechanistic explanation of the rising of the arrow of time, and what is more important, of the hierarchical organization of this particular system. Just to give you a flavor of what you get with that, this is again HCP. What you see is the example of before, but now characterized with inside out. It's consistent. Now I compress all the tasks here. All the 7 cognitive tasks are here, and compare it with rest. You see that's really cognition implies more asymmetry, more hierarchical organization, and that is perfectly captured, model-free, wise. With inside out, we compare also here for functions because we have resting state in 3 Tesla and 7 Tesla, and it's the same case. But the most beautiful case is this condition that was not analyzed before, which corresponds to the case of watching a movie. It's with the 7 Tesla equipment. And what you see here is something that was very astonishing for us at the very beginning, namely that the level of hierarchical organization, the level of non-reversibility as characterized by inside out, is lower than resting. And we were very skeptical for months about that, discussed it a lot. But then we reproduced this in another database with different methodology. We applied also Tenet here, and we confirmed that that is the case. And then we understood that where was the problem. The problem, I think, is a semantic problem. That's resting is very misleading, because resting is not resting. I mean, we are doing a lot of things during resting state, and we are doing less things when we watch a movie. So the take-home message of this violin plot is that the best way of relaxing and disconnecting is really to watch a movie. Okay, this is the model-free version. Now we do for each subject under these conditions, the model, we infer the underlying connectivity, and this is what we call the generative, because it's the causal explanation, the causal generation of the hierarchical organization. It's the generative effective connectivity, and then we show that this effective connectivity is really characterizing each condition very well. In fact, what we do is we try to classify the conditions, for example, rest against movie, as is here on the top, based on the jig or based on the functional connectivity. And what we see here on this difference, accuracy matrix and the violin plot, that we can classify much better always the conditions with the jig than with the functional connectivity. Very beautiful is there are 2 different types of movies, some Hollywood movies and some common creative movies. And in fact, functional connectivity is very bad in distinguishing the type of movies. It's practically chance label in the mean value. And the jig is really classifying the movies, and you see here the level of the confusion matrix very clearly is extremely good. So that at the end of the day, I mean, we have a way of characterizing really the hierarchical organization through the arrow of time, and to explain mechanistically why it's organizing that way. Just to close my talk and leave some space really for discussion and question, which I think is the main goal of the workshop. I just wanted to finish with some ongoing ideas, very briefly. And it's the idea of the fluctuation dissipation theorem. It's very important because it's linked with some ways of characterizing, for example, brain states in neuroscience, which in fact are strongly related with these ideas of thermodynamics that I was telling you today. but in principle, they were not motivated by that. And even I think the people, they are not aware of this relationship, that in fact, they are characterizing brain states through the level of non-equilibrium, through the level of hierarchical organization and non-reversibility. I refer here, for example, to the beautiful idea of Marcello Massimini, the perturbative complex index that most of you know, I'm sure. It's applied, it's a combination of the use of excitation, perturbation with TMS in this case, and you observe the effect of the TMS at the level of EEG signals. And he was able to show during the years that the level of the elicited complexity as a consequence of this perturbation, and this is exactly the perturbation complexity index, which is very simple measure. It's just the compressibility of this measure. So he used the Lempelsief compressibility, but it's a very good biomarker of the brain state. In fact, under different situations, consciousness is related with high elicited complexity, and non-consciousness, for example, in non-REM sleep or in anesthesia or in coma, is associated with lower level of complexity. So in principle, it has nothing to do with what I was talking about now, because it's a totally different measure. But in the context of the fluctuation dissipation theorem, we know that this is the main reason, and what they are characterizing with the proxy, which is the PCA, is in reality exactly the same that we were characterizing before. So namely the level of non-equilibrium, the level of hierarchical organization. The idea is cartoonized here. If we look at the fluctuation dissipation theorem, it's a beautiful theorem formulated by Einstein, was the first big idea of Einstein, still when he was at the patent office in Bern, so it was not in academia, but it has this great idea of relating what would happen if you perturb a system and how that's relate with the unperturbed situation. And this is called the fluctuation dissipation theory. Fluctuation means the unperturbed system. And basically what he observed is extremely simple. It's a correlation between two regions. And when you perturb the system in one of these points, and now observe what happens in the other point, which can be explained by this kind of dissipation or susceptibility, he was able to show that if the system is in equilibrium, this is equivalent. So, in other words, if the system is in equilibrium, you don't need to perturb. You can predict what would happen without perturbing. Now, if the system is not in non-equilibrium, when you perturb, you break this equality. And that means that a deviation of a violation of the fluctuation dissipation theorem, so a separation of this equality, is a measure of non-equilibrium, is a measure of hierarchical organization. And that is exactly what indirectly the PCI is measuring. Because the system has different level of non-equilibrium, then the effect of the perturbation is different, because if not, would be trivial and could not be informative, because everything is in the unperturbed state. But because we have different level of non-equilibrium, different brain states, different level of non-consciousness, then we can capture through the PCI this level of hierarchical organization. The good news is that it's not only an explanation, a very fundamental explanation of PCI, but by doing this explanation, we can do that, we think, better, because we know the real thing that we have to measure, which are, by the way, much simpler than Lempelsief. They are just correlations and elicited susceptibility. And even more, we don't need to perturb. We can do the whole analysis in the unperturbed fluctuation situation, and we can model that, and then in the model we can perturb exhaustively and calculate, just based on the unperturbed data, the violation of the fluctuation dissipation theorem. We use exactly the same type of model as before with the jig, fitting now just the functional connectivity in the easiest way. And then we perturb exhaustively the model and calculate exactly this violation of the fluctuational dissipation theorem. It's turned out that that works. So these are just two examples. For example, here, when we compare the data from Helmut Slauf and Enzo Tagliasucchi, humans, fMRI, deep sleep, N3, and awake, in terms of the fluctuation dissipation theorem, of course, there is no perturbation. The perturbation is in silico. We can distinguish very well really these two states, or coming back to the data that we were analyzing all the time, HCP and all these different conditions, rest and task condition. Again, the level of violation, so the level of non-equilibrium, the level of hierarchical organization is significantly different, as expected, by the way. So, and of course, you can get the perturbability map. I mean, how different perturbation in silico would create more deviation from the fluctuation dissipation theory. So I think I finish here. I hope that I transmitted the main idea, namely that's a key question nowadays in neuroscience, from my point of view at least, is distributed computation, and a way to go in the direction of distributed computation is, okay, how the computation, how the distribution is organized. In other words, the question about hierarchical orchestration. I hope that I was able to show that a way of capturing this hierarchical organization could be done indirectly through this thermodynamic trick of the arrow of time, that we can characterize and measure in different ways. And even, well, I didn't talk about turbulence, but it's another point. But the most important thing here is that we characterize this not only model-free, but also in a model-based, so that we have access to the causal mechanistic underlying origin of this hierarchical organization. And I finish with some promising ideas coming from the fluctuation dissipation theory, and how this is related with conventional methodologies existing nowadays in neuroscience. So thank you for your attention, and of course I am now more than happy to discuss with you or answer questions.
Thank you very much, Gustavo, for this awesome talk.
Thank you.
Have some questions from the audience.
So thank you, Gustavo, for the very nice talk first. And I was curious, when you say you talk about hierarchy, what do you have in mind? Is it like time scale hierarchy, or is it mainly anatomical hierarchy?
No, what I have in mind is a functional hierarchy. So of course there are many studies on anatomical hierarchy, and of course, I mean, as you know, anatomical hierarchy shapes the functional hierarchy, so they are related. But the main goal of our framework was really functional hierarchy. Therefore, what I mean in concrete is the level of asymmetry in the information flow. Whatever you measure the information flow, for example, just to be concrete, you can measure this in a very extremely cheap way, functional connectivity, and that will be basically but we cannot see asymmetry there, so you have to do a little bit more. So Grange causality or whatever, but it's functional in hierarchy.
Any other? I have a question. Like, I think it's very elegant and beautiful, this way of like relating this measurement with the complexity of the task, and always the social tasks were the ones that were like the more complex, or at least the ones that have more hierarchy. Do you think that that's because in those kind of tasks you have to pay attention to a lot of different cues? Like maybe if you are like thinking in something very focused, you're only doing one thing, that it's complex, but it's only one thing. And maybe in social interaction, you need cues for your from your vision, your audition, from any other. Do you think that that's why that social interaction is always on top?
Exactly. I think that is the right intuition. I mean, remember that the hierarchy implies that we have more asymmetric pairs, asymmetric connections. So the more computation you need for the task, so, and as you properly say, I mean, in social tasks, we need probably auditory information, probably we need memory information, we need visual information. So all those pairs of interaction will be more and more asymmetric because they need to do something in concrete, and therefore they will drive the asymmetry high and consequently the hierarchy high. And yeah, I mean, I think the hierarchy is indirectly reflecting the degree of distributed computation, a specific computation that is associated with that particular task. So absolutely agree with your interpretation.
We have some questions from the virtual audience. So thank you again, Gustavo, for your great talk.
Bless you.
Yes, we have another question.
Yeah, I don't really know how to frame it, but because hierarchy, then I'm thinking like top-down signals, right? Is that hierarchical signals? But then even if you have like a bottom-up signal, like something coming from just like some sensory information, wouldn't that still be very like irreversible in a sense? And like, I don't know, I have a problem understanding like the intuition there.
Yeah, let me try to see if I got properly what you mean. I mean, first, I mean, the beauty of this framework is that we are not distinguished between top down and bottom up. For us, every pair cognition, every pair of connectivity is equally relevant, and if there is asymmetry there, it's already driving the hierarchy high. So the origin could be really what we call higher order areas or what we call sensory areas. So you can drive the hierarchy high really from the sensory areas. That is not a problem. But probably the direction of your question, I feel, is, well, this is all internal. On top of that, of all this internal asymmetry, we have a source of non-equilibrium coming from the environment, because the environment is not stationary, it's driving us in different ways, and this is creating and promoting external asymmetries, which has nothing to do just with the internal computation. And that is a very good question, because that is a thing that we cannot address so directly. I mean, we have an speculation with Johnny that could go in that direction, but still is not implemented. Perhaps a way of distinguishing the external environmental non-equilibrium with the internal non-equilibrium, the computational non-equilibrium, would be through the model. So we do a model, we analyze the level of non-equilibrium in the model, we analyze the level of non-equilibrium in the data, and then the difference between both, so the level of error, let's say, is indicative of the level of things that you were not able to explain. And those things that you were not able to explain are namely the environmental factors. So we can capture perhaps indirectly, it's an speculation, we can capture perhaps indirectly the non-equilibrium driven by the environment through the error of the model. I don't know if my answer was in your direction.
It was, thank you.
Thank you.
We have another question.
Last question. Thank you for the talk. And so I was thinking of one of the last slides that you show several tasks, and that indeed you can distinguish all of them using these measures. but I can notice that there's a very big overlap between the different tasks. So
Yeah.
I was wondering of what is your interpretation on this, that you think that across different tasks, there's an actual change of the hierarchy, a reconfiguration of the hierarchy, or instead you have always the same hierarchy in place, but there are differences in the degree of information flow across the areas that are always structured in the same way?
Yeah, very, very good question. Thank you. What that means, of course, the tasks are very different, but the measure that we are using in particular here, I mean, all the measures that I talked today about, Tenet, inside out, or even this fluctuation dissipation is in this case, they are global measurements. So basically, they are washing out the difference. So they are good enough to distinguish very different situations like consciousness, non-consciousness, like rest tasks. But between two different tasks, they look very similar. It's true. In fact, in most of the cases, there are not significant differences. But this is does not mean that the hierarchical organization is the same. I mean, the label, the global label of hierarchical organization is similar, but on the details, very different. And what that means is that we need to go into the details. So to use measures which are much more detailed in describing really where is the asymmetry going on. And that's, for example, one of those measures is the perturbability map. So the perturbability map is here, it's only shown for social, but if you compare the one of social with the one of motor, they are different. So if you look at, instead of just the mean value of the matrix, which is what I'm showing here, because I want to put just one-dimensional observable. I mean, but if you keep the matrix, the non-reversibility matrix, the inside-out non-reversibility matrix, then you will see the differences. So then you will see that working memory has nothing to do with social. In average, the level of asymmetry is the same. Therefore, looks like the global hierarchical organization is the same. But of course, in the details, they are very different. So what that means is that you need to go into the details, and it would be nice to derive another measure, because of course you don't want to work with the whole matrix because it's a nightmare. Another measure which is not washing out these differences, but they are different. I mean, so the global level of a hierarchical organization could be similar in some of asymmetry, but the localization of those particular symmetries, they are very different, of course.
Thank you.
We have one last question here.
Thank you, Gustavo. This was really, really interesting. I was wondering whether neuromodulators could have a role in the hierarchy in the sense that they could be increasing or decreasing the level of hierarchy.
Absolutely. Thank you for the question. I love the question. I don't have the results here, but we analyze it. We look, well, in fact, in the anestheticum, you see a kind of evidence of that. But we analyze, for example, manipulation of serotonin through psychedelics with the data of Robin Carhart-Harris. And of course, the level of non-reversibility changed. So the hierarchical organizations, by stimulating neuromodulators, for example, serotonin in concrete, through psilocybin or LSD, change the level of non-equilibrium reversibility. In other words, change the hierarchical organization of the brain. Yeah, it's one of the causes, probably, of changing the hierarchical organization. I think it's the main cause, is probably neuromodulation.
Thank you again.
Thank you. Thank you so much.